Hello and welcome to our presentation for data valorization. Our presentation is about customer revenue analysis made by Farzam, Juan, Lin, and me, Thomas. In this submission, we will apply a linear regression as a baseline and try to analyze and improve it on a statistical way. Secondly, we will use a decision tree model and prune it based on minimal cost complexity to address overfitting. And we also try to use search strategy to tune our tree model. Thirdly, we try to combine regression and classification model to alleviate the problem of data imbalancing. And finally, we will also explore some advanced techniques such as XGBoost and neural networks and compare all of the performance of our models. In this Google Merchandise Store dataset, our task is to build an algorithm that predicts the natural log of the sum of all transactions per user. Also to help e-commerce companies understand users' behaviors and the relationship between user behavior and transaction. First of all, we set up our environment. We use a data.table to manipulate the data since it's powerful, faster, and SQL-like format. For the processing data, we simplified the data since the size of original data is around 30 gigabyte, which is far beyond the computing resources we have. First, we only use a partial amount of the data in our work. Second, we manually drop some features that are redundant or informationless. For example, features such as network domain, region, and city all present the geographical information. And also categorical features like session ID, which has 95% of unique values. If we do one-hot encoding on these features, the complexity of our models will rise exponentially. Thirdly, we regrouped labels that in some features, bucketization for instance, and we divided the feature's operating system from 30 categories into only 6 labels with other label.
We first built a linear regression with k-fold cross-validation as our baseline. Unsurprisingly, least square regression didn't fit well, and its multiple R-square has only 19.45%. However, the summary of the model seems to have conflict with the exploratory data analysis of our previous submission. For example, according to our analysis, a hit is user's behavior that has direct relationship with transaction, but the coefficient of hit here is negative, and it usually means that there is an inverse relationship between purchasing and hit. So we tried some statistical analysis over the result. You can see the attempts we made. This is our result here. Multicollinearity is a phenomenon in which one predictor variable in a multiple regression model can be linearly predicted from the others with a substantial degree of accuracy. In other words, there are variables having linear relatedness, which makes the matrix of variables to be rank deficient. In this way, the coefficients become very sensitive to small changes and thus weaken the statistical power of our model. In our previous submission, we also found out that there is a strong relationship between page view and hit. We also try a statistical method, VIF, variance inflation factor, to detect multicollinearity and remove the predictor variables with high VIF value. The VIF, the idea of this method, statistical method, is that the variances of the estimated coefficients are inflated when multicollinearity exists. Now the summary is legitimate, and features visit start time and visit number now are statistically significant. A page view is each time a visitor views a page on your website, regardless of how many hits are generated. Page view has a strong relationship with hits, but it also contains useful information, so that why we get a lower multiple R squared when we remove future hits. We then use the fitted model to predict on the test set and get our baseline RMSE 0.463. You can see that here, 0.4628. Thank you very much. This was the end of the baseline linear model, and I hope you enjoy my presentation. This is over.
Decision tree is a powerful and predictive technique we learned in our course, so we also apply it to our dataset. We first create the regression tree, where the prediction error is measured by the RMSE. And then we plot the complexity parameter table and also the result of the cross validation. You can see our tree model is extremely complicated with the number of nodes 385 and the number of splits is more than 400. You can see here. So I'm quite sure that our tree model is in the case of overfitting. So we used another strategy we learned in our course to prune our model to reduce the complexity and in turn to increase the generalization ability of our model. After we did that, you can see our model become much simpler, and also the cross validation error here and dropped from 0.85 to 0.75. After we did that, we also tried a searching strategy to tune our model to find a better value for our hyperparameter and improve the performance. Our strategy is that we choose 3 hyperparameter and we give them um, 4 values for each of them, and we try to build all the possible combinations of the hyperparameter, and we train the model with this combination and find out which one has the best result. That's what we get here. So we choose our new hyperparameter and we retrain our model and did what we did before, and that's the final result we get, the final tree model, and it has the lowest error rate so far. After we did that, we try our optimal tree model on our test set, and we get a result of 0.426, which is much better than our baseline model. Also, we try to use the logistic regression. In our case, we try to combination the classification and the regression model together to build a hierarchical algorithm. Our idea is that in our dataset, there are 90% of the user records is zero. The purchasing is zero. So maybe we can build a classification, a binary classification model to detect whether the user will buy our product or not, and then do the regression. It's in a way to solve the problem of imbalancing data. And we train the logistic regression model with the 10-fold cross validation, and we choose the best result one as our optimal model. And after that, as for the binary classification model, we also need to choose the better cutoff, which is also crucially important for a classification model. In our case, we choose it based on the false positive rate and also the false negative rate, and we try 5 different cutoff on our model. That's the result we get here, and these things like the 0.5 is the best threshold or cutoff. And also we try to use the ROC to find the best result. And you can see here the area under the curve is almost 1. That means our regression model fitted very well. And after we do that, we build our algorithm. We first detect it has revenue or not, and then if it has, we predict the revenue. otherwise the revenue we will set to 0. And we then use the linear regression to retrain the uh, on the test set, and you can see we get a better result from our baseline. And it's also in the case of the decision tree. It's the best result we get so far.
So in this step, we want to use two other methods in order to do our prediction. The first method is neural network. We will make a multi-layer perceptron in order to do a regression task. In the first step, we prepare our dataset. We gather all the effective parameters in X, and by using one hot, we encode all the categorical data to numeric data. We should have a input which all are the numeric data, and then we have the Y as our output, which is the transaction revenue of each user. Then we will make our model by using the cross. We will make a neural network model, and here we are adding the layers to our model. In the first layer, we will have a 256 neuron with activation function of ReLU. Then we add a dropout layer in order to drop out some weights to avoid overfitting. In the next layer, we have another layer with 128 neurons and activation function of ReLU. Then we add another dropout, and at the end, we will add one layer with one neuron. In order to this neuron will just the output of this neuron will be the prediction that we're looking for, and the activation function of this neuron will be linear. So we combine our model. We tell our model that the loss function will be mean square error. Here you can see the summary of our model, and here we will fit our model. We will train our model by our data. We just have 50 epoch, but the point is that by using this method and calling this parameter, we can indicate that how much of our input data should be the validation set and how much should be the training set. As you can see in this plot, we can see the convergence between the validation loss and the training loss, which shows us the overfitting is too low, and it's very good. Another good thing is that the value of loss in both of them is less than 0.2, so we can say that we reach to a good model. Our criteria to evaluate the system and model will be root mean square error, and you can see the root mean square error for different epochs. Then we, same as what we did for the input data, we will do for our test data, and we will call the prediction by giving the input test data and get the prediction of that, and then by using RMSE method, we will have the RMSE of our neural network model. In the next method, we will use XGBoost, which is X gradient boosting. We will use a group of weak learner, which are a classifier. Then they are making a tree, and by that tree, we can calculate our regression model. Here, as you can see, we prepared our input and test data set and their output. We give it to our model XGBoosting, and we get the prediction and RMSE at the end, the root mean square error. At the end, you can see the result of all our method that we use for this prediction, and our evaluation metric is root mean square error,